is Group 7 for ECEN 757 final presentation. Today we're going to present a paper, Smoother, a smooth renewable power-aware middleware. Okay, so what's the problem? When we are using renewable power, we'll face two problems. One, the first challenge is that the high fluctuation intermittency. That is because of the unstable nature of renewable power. Imagine that we're using wind power. The windmills may not be operating all the time. So this will result in two issues. One is the rate of change of frequency. So that's basically talking about the high fluctuation is making the servers using this power unreliable. Another thing is that since we have high fluctuations, we will have a need for a large battery capacity to cope with those high fluctuations. And I would like to point out that the difference between high fluctuation and intermittency. So we can see here the section 2-1. This is the fluctuation, and the intermittency is that the section 1 here from time 0 to 2 and 2 to 4. This is an intermittency. So the difference between fluctuation and intermittency is that intermittency is having power of 0. Another challenge is that low power utilization. Look at this graph below. We can see that the red line denoting the workload demand, and the blue dotted line is the supply, the power supply. So we can see that at this point, the power supply is more than the workload power demand. So we will see that there's some power is not used. So we will just waste it. So these are the two problems that we'll face when we're using renewable power. Next. So let's talk about the gaps in existing solution. So there are lots of solutions that are trying to address the previous questions, previous problems. One of them is to, let's say we have a source of renewable power, that is wind power. One solution is that whenever we get wind power, we store it into ESDs. You can basically think of it as a battery. And then whenever we need it, we extract energy from ESDs. But what's the problem of this? It is not utilizing the wind power in real time, and it requires high battery capacity. Another way is that we're using as much wind power as possible. But the problem is that it overlooks fluctuation effects of renewable power. Another way to address this problem is that, okay, let's not just focus on the wind power itself. Let's focus on the servers who are using those energies. So now we have to introduce two information here. One is that for energy consumptions, for a specific server, we can utilize energy in two kinds of clusters. One is grid-powered clusters. We can basically think of it as a fairly stable power supply. Another one is using renewable power clusters like wind power. So that method is basically trying to move servers between these two kinds of clusters. But it would cause a large overhead of moving servers around. Next. Okay, so what's the main insight of the design, the proposed design? So this paper proposed a cost-efficient, synergized design, which is called Smoother. And another thing I want to mention is that it formulates the problem of flexible smoothing into a constrained nonlinear programming problem. We won't get into the detail, but I just want to point out. So the smoother is the proposed design. It solves the challenge, first one and second challenge with finite battery capacity. That's what separates it from uh, existing methods. So it would consist two things. One is flexible smoothing that basically solves challenge one, and active delay that solves challenge two. And we'll get into the detail later. Next. So before we're using smoother, um, let's talk about when it is worth it and when it's not. So let's talk about the case that it is not worth it. So see the blue line, which is the raw input of energy, and the red dotted line is the desired um, desired line of the energy. So if we are using a smoother at time 6, we'll have to add a vertical line here. But that's a problem, because we will have to save the extra energy to the battery at time 6 to 6.5. However, these energy here is very little. But to save this energy into the battery, we'll have to require the battery to be charged in such a long time, and that's not worth it. So how do we decide whether it's worth it or not? Is that we're using a capacity factor variance, which is calculated by this formula. We're not going into the detail of this formula, but you can always refer to the paper if you're interested. Done.
Design smoother. Next. How to address practical issues of implementation. Summary. The following are the list of slides that we're going to be talking about. Design consideration, what is FS, advantages of FS, when you do not need to use FS, what is AD and advantages of AD. Next. Design consideration. The first challenge is to mitigate the fluctuation and intermittency of renewable power sources, and the solution for that would be flexible smoothing. This is going to be further elaborated. And the challenge 2 is we need to increase the utilization of renewable energy using active delay. What is FS? FS is flexible smoothing in the smoother design. An example for that is in a renewable energy power data center where we're utilizing the wind power as our energy resource for the renewable energy. FS would use battery storage to absorb that energy during peak wind times and release it during the low production periods, which we effectively smoothing the power supply to the data center. And you see in the figure number 3 where the raw power that we get and the ideal power is represented over the number of minutes and on the x-axis as well as the power on the y-axis. This is the case where the ideal power represents the renewable power with flexible smoothing. Next. Advantages of active delay. With active delay, we have increased renewable utilization where we're directly using energy intensive tasks with really high renewable generation periods. And the cost saving, of course, with increased renewable energy, we can lower the energy cost that we previously used to operate on. And as well, the last one is the environmental impact, where we reduce our carbon footprint based on our operations so that we have more, we meet the goals for the sustainability that we have promised. Next. How to address practical issues of implementation. So the battery capacity and efficiency. We need to optimize the battery usage based on the charge and the discharge rate cycles efficiently. This would extend the battery life and make sure that the energy is available when we do really need it. The second would be workload classification and scheduling for active delay. So we would need to implement really good algorithms for scheduling jobs so they can adjust based on priorities as as well as considering the information on real-time energy and the workload requirements. And the third most important thing is real-time data systems. Implementing systems really able to process those real-time data is on energy and production and consumption is very important, but also very difficult to implement. One of the examples of tools that we could use in this area would be Kafka.
So here I'm going to talk about the evaluation of the system. Next. When we want to evaluate the system, we need to first think about what kind of metrics we want to use. Next. For flexible smoothing, we want to consider energy switching time, since we want the energy production to be smooth. Less energy switching times is preferred. Next. And here's a quick note. Flexible smoothing is most effective with high power fluctuations, while the already smooth power fluctuations, there is no too much effect using flexible smoothing. Next. So here are the examples of flexible smoothing. The above graph is power generation on different dates, and below is the analysis on switching times based on these dates. And we can first look at the first graph. So we can mainly focus on the red line and the purple line. The red line is the one with the most fluctuations, and the purple line is the one with little fluctuations. And these lines correspond to the leftmost and the rightmost two bars on figure B. And we can see that the switching time reduces about 30% for May 18, and almost no changes on May 2nd, which corresponds to the note we mentioned on the previous slide that flexible smoothing is most effective with high fluctuations. Next. So the second thing we're going to talk about is the active delay. And for evaluating active delay, we also need to determine the metrics we want to use on active delay. Next. The metrics we are using is renewable energy utilization. We basically want to use the energy we produced as much as possible. So we want higher energy utilization. Next. The quick note here is active delay works in both insufficient and sufficient power supply. Next. So here is the example of active delay applied on low power supply. And we can see from the graph that there's the blue area. Blue area is the power, renewable power supply. And the green line is the initial power consumption of workload. And the red line is the adjusted power consumption of workload when active delay and smoother is used. So in low power supply, we can first look at the red line. The red line fits the outline of the blue area. That means we utilize the renewable power very well. Next. So first, I'm going to talk about the low power supply. And we can look at the graph first. The blue area is the amount of renewable power supply. And the green line is the initial power consumption of our workload. And the red line is the adjusted power consumption workload when active delay is used. So for the low power supply, we can compare the red and the green lines. When we use active delay, we can see that the red line fits the blue area more than the green line. And thus, we can see the active delay improves the energy utilization. Next. So this is an example of high power supply. And basically, the red line fits better than the green line. So we can see they have the active delay has the same effect on high power supply too. Next. So here we're going to look at a batch workload example. In this graph, it's separated into high renewable power and low renewable power. We can see that after using active delay, the power utilization increases for every case. But since low renewable power does not have enough power supply, so we use up almost all of the energy. And that results in the higher energy utilization compared to high renewable power. Okay, I'm done.
Topics from paper related to our course. The research paper directly relates to several topics discussed in class, such as synchronization and global state, peer-to-peer systems, and replication. Next. Peer-to-peer system. The decentralization of this resource sharing and the operation, the smoother could be seen as the decentralized approach for utilizing the energy resources to the maximum. Of course, the replication is for the concepts of availability, making sure that we're having energy available through storage and workload scheduling, so that we can have a system continually operate efficiently regardless of different fluctuations in energy supply. Next. The weakness of the paper. There is a limited scope of renewable resources, meaning that this paper focuses mostly on wind energy. So it would be great if the model could be designed, or the system design could be marginalized to include other renewable sources. The other point is the real world implementation challenges. We need to include details on the challenges with economically, logistically, and the infrastructure changes and the cost of making these changes through the middleware. The third point, scalability concerns. We need to propose a solution that is able to handle different sizes and types of system, whether it's like small and versus large scale data centers, or different locations or different regions. Next. Beyond the scope of the paper. So we need to focus on cross-domain applications, where this is not just about computing systems, such as in manufacturing or transportation, where we need more renewable energy integration, which is very critical. And we also need an application to other renewable resources, where we need to research more into solar, hydro, and other renewable resources, where we could make it more universally applicable. The third point that we have not talked about is the rate of energy loss as it travels to the destination. I have not seen the paper discuss this point in the paper. Next. Thank you.